Advantages of integrating third-party hydraulic fracturing tools into CMG's unconventional modeling workflows. My name is Jim Ertl. I'm the Vice President of our U.S. and Latin America combined region at CMG. I'm pleased to introduce our presenter for today's webinar, David Moody, who is a reservoir simulation engineer here at CMG. David received his BS degree in petroleum engineering with minor in computer science from the University of Texas at Austin. Upon graduation in 2009, he joined CMG as a reservoir simulation engineer with a focus on CMG workflows for model creation using Builder and model output visualization using Results. For several years now, he has worked closely with our software developers on the continuous optimization of the hydraulically fractured well modeling features and other special projects in CMG software. He is based in CMG's Sales and Support Office here in Houston, Texas. Please stay with us until the end of the webinar, as there will be a question and answer session after the presentation concludes. Okay, so I'm going to hand off to David, and here we go.
Thanks, Jim. This presentation will focus on advantages of integrating third-party hydraulic fracturing tools into your unconventional reservoir simulation workflow. Keep in mind, this is speaking to new, enhanced ways to define hydraulic fractures. First, we'll get into the why. Why even consider integrating hydraulic fracture modeling in my reservoir simulation workflow? We'll take a look at the CMG unconventional workflow for forecasting and optimization that we have now, then get into the specifics of hydraulic fracturing. How do we represent hydraulic fractures currently in CMG? What's the difference in our bi-wing planar fractures and complex fractures? What are some benefits of integrating hydraulic fracture modeling results? We'll compare a couple solutions CMG has produced thus far, and even show a demo of how to import conductivity data from one of these tools. Finally, we'll conclude this presentation with what we think this integration offers to everyone in the unconventional world. Why integrate hydraulic fracture modeling? First of all, for a more accurate distribution of fracture conductivity. They take into account actual volumes of pumped fluid and proppant, the true geometry of the fracture, depending on the modeling software you use to create your hydraulic fractures. Also take into account geomechanics specifically associated with hydraulic fractures. Finally, we constrain the reservoir simulation with real and achievable completion designs.
We'd now like to ask for audience response to the following question. How familiar are you with CMG's unconventional workflow? Very familiar, somewhat familiar, or not familiar at all? We're going to give you a few seconds to answer here, and then I'll reveal the percentages as they stabilize on the screen here. It looks like 58 to 60% of you are somewhat familiar with these tools. 32% were not familiar at all, and 10% are very familiar. So it's good. We're going to break some new ground here. Back to you, David.
Thanks, Jim. So for those of you not familiar with CMG's unconventional workflow, here's a brief overview. First, we'll choose the simulator with appropriate physics for what we are trying to model. Do we need IMAX? Do we need GEM? Once we know that, we can move on to building a base model, creating our grid, defining reservoir properties for our matrix, as well as natural fractures if they exist, create a fluid model, define our relative permeability, initialize our model with fluid contacts and initial pressure, and finally, define our wells and production data. Next, once we have this base model built, we can perform a sensitivity analysis as well as a history match. What if I am unsure of my reservoir properties like porosity or permeability? How big of an impact does it have on my historical production if I vary these properties within a certain range? After we find a range of values for these properties that bounds our historical production, we attempt a history match. We tell CMOST to vary these given properties within a certain range of values and give us feedback on which values match our historical production best. With these history matched models, we can run forecasts to estimate our ultimate recovery. Finally, we assess uncertainties to fully understand the accuracy of our predictions. But what about hydraulic fractures? Where do they fit in? How does CMG handle hydraulic fractures currently? One way that we can represent fractures is the bi-wing planar fracture. You first create a fracture template where you assign most of the hydraulic fracture properties. What's my permeability look like in the fracture conduit? We can either set a constant permeability along the fracture or apply a linear gradient decreasing from the perforation out to the tip. What's my effective width and height along the fracture? How far does my fracture actually extend into the reservoir, or what's the half length? Once we have a template defined, we can create the fractures by specifying a fracture spacing. This assigns the template properties to multiple fractures along the wellbore. You can also use multiple templates with all different properties. You do not have to use just one template for the entire length of the wellbore. Another way we can create fractures would be the complex fracture. In Builder, you can import microseismic data, which consists of three-dimensional points marking microseismic events, each with a value for moment, magnitude, and confidence. You can then use this data to create, in essence, intersecting transverse fractures based on the values for each moment, magnitude, and confidence. In fact, you can also vary the ranges of values to be filtered for each one of these properties you can see here. Some of the events on the outside do not create fractures due to their property values. Fracture width and permeability are then assigned on a per stage basis.
We have a second polling question for you out of the three that we're going to ask today. And that is, which of these types of fractures have you used in your reservoir simulation modeling of your unconventional wells? Do you or have you used planar fractures? Have you used complex fractures? Maybe both in the same model for a given well, or none of the above? I'll give you a few seconds here and we'll reveal the audience response here. It looks like planar fractures sort of dominate the response of about 44%. 9% of you have been employing the use of complex fractures. 26% of you are using both in the same model, maybe for the same well, maybe for different wells in the same pad. And then none of the above is 22%. Very interesting. Okay, David, back to you.
So how could we make this better? What could we add? A couple years ago, we received a call from Anadarko. They were using our software to model one of their unconventional fields. They mentioned they were using a separate hydraulic fracture modeling tool and wondered if we offered a way to bring that data into a CMG model. At the time, we said not currently, but that sounds like a great idea. So what do tools such as these have to offer? Well, here's a small snapshot of what goes on under the hood of most of these tools. You can input rock properties directly from log data. You can generate the closure stress profile, take into account 3D fracture geometry, iteratively couple the distribution of fluid pressure to proppant concentration, and compute leak off at each point along the fracture surface. Also, they incorporate the effects of secondary shear fractures. All of these are reasons we want to integrate this data into our models. So we needed to develop a way to import this data from all of these tools. How did we do it? We worked to design a file format that these tools could export and CMG could then import. This file contains essentially a long table of values for conductivity at each fracture. This simple cross-section of one hydraulic fracture at a given perforation cluster we can use as an example. So as we see here, depth is increasing downward. Offset is simply a measure of distance away from the wellbore horizontally along the plane of the hydraulic fracture. The colors represent values for conductivity ranging from the higher red values in the center down to lower blue values toward the tip of the fracture. Using this new file format, we can take advantage of all this conductivity data for each fracture along the wellbore and create planar fractures in our CMG model. We can do this one of two ways. The first is taking advantage of what is already in place with our bi-wing planar fracture templates. Taking the file exported from any hydraulic fracturing tool, we read through the long table of values and for each fracture find the minimum and maximum conductivity. A template is then created for each fracture with separate values for permeability calculated from the imported conductivity, fracture width, height, and even half length. This time, we set the permeability to be a linear gradient decreasing from the wellbore perforation out to the tip of the fracture. All of these properties are read directly from the exported file. In the end, we have a separate fracture for each cluster, each with property values calculated by these other tools. The second is to go beyond just finding minimum and maximum conductivity and actually importing the full array of values. Similar to the linear solution, the width and height and half length are all defined the same. The permeability, however, is assigned using an array of values imported directly from the file, as you can see here. Again, taking advantage of property values calculated in other hydraulic fracture modeling tools that take into account many additional features.
And now we're ready for our third and final polling question of our session. And that question is, were you aware that Builder can import conductivity data from third-party hydraulic fracturing tools? And the results are coming in pretty quickly here. It looks like a majority of you were not aware of this, so it looks like this webinar is a timely topic. 60-some-odd% of you said no, you weren't aware, and about 40% of you said that you were. So I'm glad we're expanding your knowledge base. Back to you, David.
Now a quick demo to show the process of importing one of these files into Builder. Here we have a simple unconventional field that covers about 700 acres. This model has several layers in it, totaling about 300 feet thick. We can see we have some more thick layers up top than down below. The permeability in our reservoir is a constant 300 nanodarcies everywhere. We have our porosity defined, which ranges anywhere from about 7.7% up to about 8.5%. We can see the lateral length of our wellbore is approximately 4,000 feet. So we have our model here. It's fully built and it's ready to run, but now we want to add hydraulic fractures. If we open our hydraulic fracturing wizard, we see a few tabs here. The first tab is for our fractures, where we create fracture stages based on templates we have defined. The next tab is where we create these templates. We can easily create a new template here, fill in our fracture width of 0.01 feet and intrinsic permeability of 10 darcies, which comes out to, as you can see, 50 millidarcies for a 2-foot wide block in the model. In order to have a model that runs very quickly, we use a 2-foot wide grid block by default, but still preserve conductivity by scaling permeability in the fracture block, as well as inputting an optional value for tip permeability here. We can set that as 1,000 millidarcies or 1 darcy. Here we also need to define our fracture orientation, which for us here will be in the I direction. We can change the number of refinements in each horizontal direction. If we wanted a more fine grid, we could set this to maybe be 9 by 9. Our half length we set here is 350 feet. And finally, we set our number of layers up and down that we want to refine, which effectively gives us our fracture height. So we can set 5 going both ways here. If we hit apply, we can go back to the fractures tab, click the date for well 1, and create a new planar fracture stage. Here, we can select the fracture template we just made, input our fracture spacing here of 200 feet. We hit apply, and we see very quickly, just within a few seconds, we can set up uniform fractures all along the wellbore here using just one template. We can visualize these in 3D. I'll pull these up here, as well as switch to permeability, change the color scale so that we can see just the fractures. So now we see that we've created all of these fractures along the wellbore using one template. So this is how we can set up fractures currently in CMG, but what if you have data coming from another third-party tool? We can see how to import that here. If we go back to the hydraulic fracture wizard, we can click the stage we just made and remove it so that we can add the new stage. We'll click the date for well 1, and we see this, this third option here says to import a fracture stage. So we can go choose our file, which here we'll choose the uniform file. And again, with just a couple clicks, we can bring in several fractures from third-party tools. And they're all set up completely with different templates for each fracture as well. I think it's easier to visualize here in 3D. Again, we'll change the color scale so we can see just the fractures. So now we see that we've created all of these fractures just by importing a file from a third-party tool. We can see that we actually have a higher density of fractures closer to the heel of the wellbore and fewer fractures near the toe, as well as lower conductivity in these fractures toward the toe. So this would give us an even more realistic representation of the fractures in the model by importing a file from a third-party tool. We can also import the permeability using the full array of conductivity values. If we go back to this stage, we'll remove these so that we can bring in our non-uniform fractures. Again, here we'll say import fracture stage, and we'll simply choose our second file, non-uniform. And again, just a couple of clicks, and the file comes in, all of the different fractures. This time, however, we'll be able to see that we have a more realistic distribution of conductivity throughout the fractures. Change the color scale again. So here we can see, again, we have fractures in the same place, but we have much more realistic distributions of conductivity throughout each fracture stage. So this is a demonstration of how we can import the fractures, but let's take a look at some results. So here we have 3 cases open. The first case was the first demonstration I did, where we created one fracture template and assigned it everywhere along the wellbore with a 200 feet fracture spacing. So I called this the averaged hydraulic fracture case, just simply implying that each one of these fractures are the same values. The second case here is the first file that we imported, where we brought in uniform hydraulic fractures, meaning a linear gradient from wellbore out to the tip of the fracture. And finally, the third case here is the non-uniform import, where we take advantage of the full array of conductivity values. So here we're visualizing pressure, looking aerially down on the wellbore. We can animate this through time, and we see that over the course of just 1 year, we see a pretty drastic difference in our pressure distribution along the wellbores. In the first model, we see what we would expect, a fairly uniform distribution of pressure along the wellbore, since each one of these fractures is set up with the same permeability and the same half length and height and everything. The second model here, again, we see a much different pressure distribution because we have a higher density of fractures as well as higher conductivity within those fractures near the heel, as opposed to the toe of the well, where we don't have as many fractures, and as well we have lower conductivity. And the third file here, we still see differences in pressure than from the uniform import, because we take advantage of the full array of conductivity in the fracture, on the fracture surface. So this is pressure. Let's take a look at production. Before we do that, we have when I show some plots of production, I want to make sure that we have these 3 cases defined that you'll see in the legend. The first one, again, is the averaged hydraulic fracture case, where we create symmetrical hydraulic fractures that are generated using the hydraulic fracture wizard inside of Builder, where we create one template and assign that same template all the way along the length of the wellbore, having a linear conductivity gradient from the wellbore to the tip of the fracture. The second case, we imported a file from a third-party hydraulic fracturing tool and we generated, again, symmetrical hydraulic fractures with a linear conductivity gradient from the wellbore to the tip. This is different from the first case, though, because each one of the fractures is different, though within one fracture we have symmetrical half lengths on either side, as well as this conductivity gradient. The third case, we imported a different file, but we imported the full array of permeability. So this created asymmetrical hydraulic fractures. Again, the file was generated by third-party software. And this takes advantage of the variable conductivity distribution. Here we see a plot of cumulative gas production for each one of these cases. I did include one case where we have no hydraulic fractures in our model at all, and looking at cumulative gas over just 1 year, we see we only have about 4 million cubic feet of gas with no hydraulic fractures. Now, when we incorporate hydraulic fractures in our model, in the averaged case here, we can see that where we have the equivalent averaged fractures, we can see that it overestimates production compared to the imported cases. Then if we compare the uniform import versus the non-uniform import case, the non-uniform imported case has much more reasonable and realistic production values. Let's focus on the averaged case. What if we're unsure of the estimates for our hydraulic fracture conductivity and half length? If we vary these properties, say plus or minus 25%, we find the impact on gas production over only a year is already 35% on either side. If we compare this to the uniform import case, we actually notice a significant decrease in uncertainty to about 18% difference above and below our cumulative gas production. Finally, taking a look at the case where we import the full array of conductivity values, again doing the same thing here where we scale all of the values plus or minus 25%, we see that our uncertainty here is brought down to less than 5% on either side. So what are we trying to say here? We think that integrating hydraulic fracture modeling results from third-party tools into your current unconventional workflow is more theoretically accurate. Instead of using ballpark estimates for fracture properties such as conductivity and half length, you can now take advantage of physics and geomechanics-based calculations. This reduces uncertainty in your simulation results, and with this reduced uncertainty, you can better improve your NPV by optimizing this hydraulic fracture design beforehand. And finally, as you've seen in the demo, it is very quick and easy to set up.
Okay, thank you, David, for that very informative presentation. We're now going to attempt to answer as many questions as possible from the audience. Okay, first question, what data, hold on a second here. Sorry, I'm new to this particular application. First question, how can we generate hydraulic fractures into our wells in our grids by using Builder? Well, I think we've kind of seen that, the different techniques that we've got for doing that. But just to reiterate, we can generate hydraulic fractures from scratch just within Builder if you're willing to start the process with uniform fractures, common fracture half lengths, etc. But as we've shown here today, if you want to work with what the completions engineers are working with out in the field to design their fractures, we obviously can import that as well. So that's one particular question. Next question, we would like to use the planar fractures template. There seems to be a need to model asymmetric fracture lengths. Is this something that could be done in the future without using the complex fracture template? I think that's a great suggestion, and there's probably no real reason why we couldn't do that. We just haven't implemented that yet, so we will consider that as a new feature request to add to the growing list of ideas that we always get from our existing users. Next question, Barree, thank you. With complex fractures, microseismic data is not able to see where proppant goes, and the geomodeling with assumed natural fractures crossing criteria is a question. How is conductivity assigned in those cases? Well, when we're working with the microseismic data, if we're going to use that information to delineate an SRV that we think the data tells us it's complex fracturing, currently we're just going to assign a constant permeability and width to those fractures. We don't have any gradient capability in that section of the model building process at this point, But again, that's something that we could look at as a future addition to the process. I think we're coming close to, okay. Can we model horizontal well re-fracs by placing and using planar or complex fracs template in the wells in recurrent data? How do current CMG users history match re-frac production in terms of representing hydraulic fractures? I believe the answer to that question is yes. We can certainly simulate re-fracs, so we can add the grid refinement that's associated with each fracture in recurrent data to simulate that process.
And just to add to that, when I was doing the demo, I showed how you click on a completion date for the well to add fractures. So if you have multiple completion dates for that, you can add fractures at later dates throughout the simulation. It doesn't have to be at the beginning.
Very good. Another question, does this work with both IMEX and GEM? The answer is absolutely, and now also works with stars. Okay, there have been some interesting applications of the fracture networks that get created by hydraulic fracturing to be used as a way to expose formations to heat and to surfactants and other types of processes that would require even the use of stars in some cases. So the answer to that is absolutely yes. Next question, which data format has the input file? Well, it is an ASCII file, okay? And that format can be shared with anyone, both software vendors and CMG users. That's not a problem. But it's basically just an ASCII file with XYZ location and conductivity information, something we call offset. It's a pretty simple file setup to create that file. David, do you want to comment on any of that?
No, that's right.
Okay. I'd be interested to see the structure of the file. Yes, we can definitely share that with anyone, so no problem there. Which third-party tools can we use to import complex fractures, the complex fracture conductivity length into Builder? Well, actually, most of the software that's out there on the market today really supports the generation of planar fractures. And right now, this ability to import from those packages, and we're going to show you a list on the screen of which products currently support this this data format. Really, these are all planar fracture generation tools. So GOHFER, FracProPT, STIMPRO, StimPlan, FracPredictor, which is from a new company called FracGeo, and MFRAC from the old Meyer and Associates tool that's now owned by Baker Hughes. They're currently working on adding that export format for MFRAC. We have talked about packages like M-Shale that can apparently export a complex fracture network. That hasn't been finalized yet, but we're certainly willing to consider that. And there's a lot that people are doing even with our own geomechanics package, which can model fractures opening up in a natural fracture network, which could be planar or complex. We're going to be talking more about that in the future, but we hope to have a tool here in the near future where we can actually model the creation of either complex or planar fractures, including prop transport. So that's something that's coming. On to the next question here. What exactly uniform and non-uniform means?
Okay, I'll answer that. So I tried to demonstrate in the demo, but the main difference is the conductivity distribution. So in the one case, we import several fractures, but we assign a linear gradient of permeability starting from the wellbore and extending out to the tip. That would be the uniform case. Whereas in the what we call non-uniform or variable distribution is where we bring in the full array of conductivity values and assign them to the surface of the fracture.
Well, let's go with a couple more here. Okay, another question here from Tyler. Can you import 3D fracture distributions and geometries from geomechanical simulators. And by that I assume you mean products like from Itasca and Abacus, etc. Actually, we could, if they adopted the ability to generate these data exchange files, and we're certainly willing to share that with them as well. So really, we don't have any preference or concerns about connecting up with any third-party software to do this. So yes, we can't do it today, but we're certainly willing to consider doing it. Okay. Next question is, thanks for the presentation. My question is how to handle the problem of fracture closure. Okay. Well, I think closure is something usually associated with the end of the pumping job and what happens when you try to keep proppant from dropping down in the reservoir, etc. Maybe, though, I think what we're talking about here more is what about the effect of changing effective stress on the proppant permeability and so on and so forth. And that's something that we always try to capture in our models, either as a function of just pressure with compaction tables, or if we use our coupled geomechanics, we can actually set up to monitor the change in permeability and porosity of the proppant and the natural fracs and the matrix as a function of changes in stress. So you really have either way to do that. The import from the hydraulic fracturing software is sort of initial conditions, but beyond that, we can allow things to change with our other features in our reservoir simulator. So that was a very good question. I think we'll take one more here and then call the webinar to a conclusion. How do you define relative permeability and flow physics at fracture planes or grids, which are different from matrix properties? That's fairly easy to answer. Basically, rock regions inside a reservoir simulation model can all have their own unique rel perm and capillary pressure curves, and so the prop fractures and the natural fractures and the matrix in one of these unconventional well models, we typically assign different sets of rel perm curves to. And for the prop fracs and the natural fracs, that's typically straight line rel perms, although it doesn't have to be, and no capillary pressure because the permeability is so high. And then the real question is, what about in these very, very tight matrix rocks? What sort of relative permeability and capillary pressure curves can we assign? That's a very difficult problem because we can assign anything, but as you know, it's very difficult and expensive to measure this stuff in the lab. So one thing we like to do is allow the history matching process to back into what matrix permeability, cap pressure, and rel perm curves should look like by using Corey functions and allowing ranges of values for all of the endpoints and the exponents to help us sort of home in on what the correct values for those items should be. And of course, the longer your production history, the more likely that you might have multi-phase flow in the reservoir rock itself. And so you're going to learn more over time what those correct values should be. Well, I think we're about to the end of the presentation. I'm sorry we couldn't get to all of your questions, but we look forward to receiving more, and we will get back to you when as soon as possible with those. So thanks David for your presentation. I hope you now all have a better understanding of how we've enhanced CMG's unconventional workflow by importing variable conductivity and even variable half-length fracture conductivity data from the leading tools in the industry. We do want to remind you that we provide training in several different CMG offices around the world on this subject and many others. And you can go to cmgl.ca to look at the training schedules, or you can contact us at training@cmgcl.ca if you have very specific needs, because we can even create custom courses for you if that's a better situation for you. And again, I want to remind you the entire webinar was recorded, and it's going to be made available for download at our website within the next 24-hour period. So that concludes today's webinar. I look forward to engaging with many of you in the near future on follow-up discussions along these lines, and look for our next webinar, which should be scheduled very soon after the new year. Thank you and goodbye.